In this training, we'll go into more detail of the multi-user MIMO, long-distance OFDM symbol, and the 1024 QAM and how it all works within the 802.11ax standard. With 802.11ax, we have access to both OFDMA and multi-user MIMO. Each has its strengths and weaknesses. Single-user MIMO was introduced in 11an. It increases the Wi-Fi speeds by allowing a pair of wireless devices to simultaneously send or receive multiple data streams. Multi-user MIMO was introduced in 11ac. It theoretically allows multiple frames to be transmitted to different receivers at the same time and at the same channel, using multiple spatial streams to provide greater efficiency. For 11ac, it was the only available on downlink. With 802.11ax, it will work with both uplink and downlink streams. In multi-user MIMO, if you have a 4-stream AP like a 720 or a 710 and a 4-stream laptop, it can transmit all 4 streams at the same time using beamforming to direct the beams to the client. However, today this 4-stream laptop really doesn't exist due to power consumption and the overall benefit. By using multi-user MIMO, I could have a PC or smartphone using 2 streams each, and other clients with 1 stream each. Multi-user MIMO allows me to beamform my transmission, allowing 2 streams to be used for a PC, assuming that it has multi-user MIMO capabilities, and 1 stream to a smartphone, using another stream for a tablet as well. In multi-user MIMO, I am beamforming the stream direct to the client, which is very different than single-user MIMO, where the streams are used to increase transmission capabilities. In OFDMA, they are getting different chunks of the spectrum, which are divided up into resource units or RU tones. So to be clear, multi-user MIMO is very different than the multi-user of OFDMA, where they are getting different chunks of the spectrum, which are divided up into resource units or RU tones. However, OFDMA and multi-user MIMO theoretically can be used in conjunction when an 802.11ax device and AP are in operation. So when should I use OFDMA or when should I use multi-user MIMO? This chart shows the strengths and weaknesses of both technologies and when to use them. These are 2 complementary multi-user technologies to serve multi-users concurrently. With multi-user MIMO, I need to know where each client is, so I can talk to them in 2 different directions simultaneously. To do this, the AP needs to do some work to figure out their location. This is accomplished through sounding. The sounding process takes about 1 millisecond, which is a long time in the Wi-Fi world. If I spend 1 millisecond trying to figure out a client's location, I need to have at least 10 milliseconds to transmit my data to get the benefit for using that sounding time. If I do all this work for 1 millisecond and then transmit 100 microseconds of data, it doesn't make sense as my overhead is too high. What this means is that I need to have a lot of data to transmit. So when there is lots of data to transmit, such as downloading a large video, multi-user MIMO is very useful. With OFDMA, there is no sounding overhead for either download or upload OFDMA. I don't care where my clients are, I just allocate a chunk of the spectrum, so there is no concept of sounding within OFDMA. Transferring data. If I break a big truck into smaller chunks, which means I am transporting little boxes or small amounts of data, OFDMA is very applicable. If I have a bunch of phones doing Wi-Fi calling, I'm better using OFDMA. It doesn't make sense for me to do multi-user MIMO to those clients because I only have a small amount of data. But if 10 clients are downloading 4K movies, I'm better off using multi-user MIMO to those clients. 2 different scenarios and 2 different use cases, and both are useful in their respective environments. Number of concurrent clients. OFDMA allows the AP to talk to multiple devices at the same time. In the 11AC standard with single-user MIMO, I had to talk to only 1 device at a time. Now I can have parallel conversations with both devices at the same time, from 9 clients with a 20 megahertz channel up to 74 clients with a 160 megahertz channel. With MultiUser MIMO, my number of concurrent clients is limited to 8. Range improvement. With OFDMA, I can improve range because of power spectrum density. We will talk more about spectrum density next, allowing us to better understand the OFDMA ability to concentrate power. MultiUser MIMO does not offer range improvements. Latency. OFDMA tends to decrease latency, while MultiUser MIMO increases latency. And lastly, the effective ranges. OFDMA is effective at all ranges because of its long OFDMA symbol. MultiUser MIMO is only effective at close to mid-range, so it's not good for long-range deployments. So how does OFDMA increase range? A cellular base station covers a much larger area than an AP, yet a cell phone with Wi-Fi has trouble talking to an AP that might be 100 plus meters away. But the same cell phone does not have problems talking to the LTE base station that might be a half-mile away. How does this work when it's the same battery, hardware, and wireless antenna? So let's take a look at that further. Frequently, every problem that is attributed to Wi-Fi is blamed on the AP and not the client. We often run into situations where I'm at one corner of my house that is far from the AP, yet the phone picks up the beacon from the AP and displays the SSID. However, when I try to connect to the AP, it's not successful because it's too far from the phone. Although the AP will broadcast a higher dBm, the phone is only transmitting 15 to 20 dBm. There is a typical 10 dBm gap between the uplink and downlink. The AP can talk to the phone, but the phone won't talk to the AP. People blame it on the AP, but the problem is that the phone can't shout as loud as the AP. Let's look at an example. Let's say I have a power amplifier with a certain amount of power that's available to me. If I'm using 80 megahertz band, that power is spread over that 80 megahertz. With OFDMA, I can give a 2 megahertz channel versus an 80 megahertz channel to a device, which puts the same power in a much smaller spectrum. This is what we're showing on the right side. The green rectangle is my power, and the power is spread over a much narrower band. Now the signal looks very thick and tall. It's going to be much stronger than the noise when the signal reaches the AP. This is how LTE does it today. The same phone can talk to a faraway base station because it's using a narrower spectrum to talk. In this section, we'll look at now 2 other 802.11ax enhancements that improve efficiency, which is long OFDM symbol and 1024 QAM. The OFDM signal was originally designed with indoor Wi-Fi in mind. In an indoor environment, multipath reflected RF signals were expected to come back very quickly. The pre-AX OFDM symbol was composed of a data portion that was 3.2 microseconds long with a guard interval of 0.4 or 0.8 microseconds. When using Wi-Fi outside, because of the increased distances and increased delay of reflections, multipath presents a problem. Long OFDM symbols help correct this problem. Let's look how OFDM long symbol improves outdoor operation. In 802.11ax, it maintains the same channel width as 11ac, such as 20, 40, or 80 megahertz. However, it increases the fast Fourier transmission, or FFT size, by a factor of 4. This means there are 4 times more subcarriers in a given bandwidth, resulting in a 4 times reduction in the subcarrier spacing. So we go from 312.5 kilohertz to 78.125 kilohertz subcarrier. This gives us frequency domain efficiency and capacity increase as it provides 4 times more the tones or subcarriers to allocate to multiple users. However, it comes with a price. The narrower subcarrier spacing is more sensitive to frequency offsets, phase noise, and sampling clause offsets. In the time domain, this translates to a 4 times longer OFDM signal. The data portion has been extended fourfold from 3.2 microseconds to 12.8 microseconds, and the guard option can be extended from zero point 0.4 or zero point 0.8 microseconds up to 3.2 microseconds. This allows us to cover both indoor and outdoor operation. The outdoor operation is handled by using the new extended range single user packet type. The way we can make this work is by looking at the bottom graph. Here we quadruple the duration of the red portion. Instead of 0.8 microseconds, it's now 3.2 microseconds, which means it can tolerate reflections coming from much larger distances. The yellow portion has been increased fourfold to 12.8 microseconds, which gives a lot of outdoor multipath tolerance and keeps the overhead the same. The yellow and red portion constitutes one OFDM symbol. This increase in size is called long wave OFDM symbol. As a result, it's better for the outdoor deployments, which means it can now mount your AP at a much taller height to cover a wider area. How does this longer OFDM symbol affect indoor deployments? We know that indoors do not need long guard intervals. We use the long wave OFDM symbol but keep the red portion short in the indoor use. This decreases the overhead because it is much longer yellow followed by a small red. Ruckus APs are optimizing numerous parameters. BeamFlex Plus will try to maximize the throughput first, along with determining which modulation coding scheme to use, whether to use MultiUser MIMO or OFDMA, and which size of guard interval to be used in this environment. When the AP is mounted outside, it will try to maximize the throughput first. It will try the 0.8 microseconds because it will maximize the throughput. If it realizes it doesn't work well, it will try the 3.2 microsecond guard interval instead. Another 802.11ax enhancement is 1024 QAM. Quadrature amplitude modulation is a highly developed modulation scheme used for the communication industry in which data is transmitted over radio frequencies. By varying the amplitude of the signal as well as the phase, Wi-Fi radios are able to construct a constellation diagram that shows the values associated with the different states. In the animation, this shows a 16 QAM signal. By varying these sinusoidal waves through the phase and amplitude, radio engineers can construct signals that transmit an ever higher number of bits per hertz. Systems designed to maximize spectral efficiency care a great deal about bits and hertz efficiency, and thus are always employing techniques to construct ever denser QAM constellations to increase data rates. Higher QAM levels increase throughput capabilities in wireless devices. The new Wi-Fi 6 or 802.11ax standard incorporates 1024 QAM, with each symbol encoding a larger number of data bits when using dense constellations. This translates to better throughput at a physical layer at 25% higher capacity with 10 bits per symbol versus 8 bits with 256 QAM. More bits equals more data, and the payload delivery of data is more efficient, like having a bigger truck. With billions of connected things expected within our networks, higher wireless throughput facilitated by 1024 QAM is crucial to ensuring quality of service in high-density locations such as stadiums, convention centers, transportation hubs, and auditoriums. Applications such as 4K video streaming are expected to drive internet traffic to 278 petabytes per month by 2021. 802.11ax also introduces two new optional modulation coding schemes, MCS10 and MCS11. Due to the denser constellation, a 3 dB tighter error vector magnitude or EVM limit is applied. So we're looking at a negative 35 dB EVM versus a negative 32 dBm for 256 QAM. 1024 QAM can only be used with 242 subcarriers or tones or larger. This means that at least a full 20 MHz channel will be needed for 1024 QAM. As mentioned, two new modulation schemes, MCS10 and MCS11, have been identified with 802.11ax, providing increased data rates when 1024 QAM is used. Here you can see with one spatial stream the perceivable rates based on tones or RU sizes rather than channel width of previous standards, since OFDMA can divide channels into subcarriers or resource units. So in summary, 802.11ax has two forms of multi-user capabilities, with OFDMA and the use of MultiUser MIMO. Long OFDM symbols will increase efficiency in outdoor deployments, and the new 1024 QAM symbol has been added to the Wi-Fi toolbox.